Okay. So now we will be seeing the optical properties of colloids. There are three types of properties which are existing because of the size which is peculiar in the case of colloids. One is optical properties, another one is kinetic properties, another one is electrical properties. So in the optical properties, we have got one phenomena called as a Tyndall effect. So when a strong beam of light is passed through the perpendicularly through two solutions. So one is a true solution where it is existing as a what you have got a regular solution, they are transparent in nature. The second one is a colloidal solution which we are studying. So if you are placing against the dark viewing against the dark background, the path of the light is not visible in the case of true solution. This is one thing what we are going to observe. Whereas the path of the beam is visible in the case visible because it is getting scattered in the case of colloidal solutions. Further, it is forming as a shadow or a beam or a cone at the dark background. So we can view it as it is depicted in this particular picture. If you are passing any light source through a true solution, it will pass 100% without any hindrance. Whereas when it is passing through a colloidal solution, it will scatter in all directions. That is the reason it produces its path. And you can view it when it is observed through the dark background. This effect is called as a Tyndall effect. This phenomena of scattering of light by the colloidal particle is called as a Tyndall effect. The illuminated beam or the cone formed by the colloidal particles that is already present in a solution form, and it is called as a Tyndall beam or a Tyndall cone. The Tyndall effect is due to the fact that colloidal particles are scatter light in all directions in the space. So that scattering of the light illuminates the path of the beam in the colloidal dispersion, which is a peculiar in the case of a colloidal dispersion not exist in a regular solutions. It means when you got any polymer or surfactant whose molecular weight is more and the molecular size of that particular value is in the range of colloidal region, they will produce this optical property, and we can distinguish whether it is a regular solution or colloidal solution. Generally, the colloidal solutions little bit hazy to appear, not like a transparent as that of your liquid real solutions. Another one is a turbidity that can be observed by using a spectrophotometer, because we are going to have some concentration of this one present. As the concentration of the polymer or surfactant is increasing, turbidity will also be getting increased. Turbidity is against the transparency. When it is turbid, the liquid is not transparent. Another one is light scattering. We have already seen in the Tyndall effect, the scattering of the light is present in all directions, which can be observed in the dark field microscope or ultra microscope. In the dark field microscope, we are going to act against the light source in the 90 angle, and we are going to detect them beams. Because the light is scattering in the all directions, we are putting a detector in the 90 degree angle. So wherever we are putting the source in one direction, at 90 angle we are putting a detector. Even in the 90 angle also, the source light will be detected in the dark field microscope. So in the ultra microscope, we are going to have this phenomena observed. Whereas turbidity can be observed by the spectrophotometer, and the Tyndall effect will be viewed visually directly with the dark background. Now, we are going to enter into the second phenomena, and property is called as kinetic property of a colloid. In that we have got 5 different properties. One is Brownian motion, the second one is diffusion, third one is osmotic pressure, fourth one is sedimentation, fifth is viscosity. So the kinetic properties of colloidal, this one related to the motion of the particles when they are moving with respect to the dispersion medium. Now we will be seeing one by one. All the 5 you are going to memorize. You will be asked separate questions in 5 marks, or you will be asked to list them in 2 marks, or you will be asked 1 or 2 more properties in 10 marks. And entire portion you are going to get in GPAT. Because of that reason, you are going to have this particular physical pharmaceutics portion around 10 questions in the GPAT. Better to assimilate now itself. The motion may be thermally induced most of the times by the Brownian movement or diffusion or osmosis. Gravitational force induced, that is sedimentation, and applied externally, it means by using a external any surfactant or a material which induces the viscosity. So first we will be seeing a Brownian motion. We know that the particle which is having a size less than 5 micron, they will be traveling as they like. So the colloidal particles undergo the random collisions. They will be hitting to each other. With the molecules of the dispersion, in the molecule of the dispersion medium, whatever we are using as a solvent, and follow an irregular and complicated zigzag path. They will be having a complicated zigzag path. So if the particles up to about 5.5 micron diameter are observed under the microscope, the light is scattered by the colloidal particle is viewed in the ultramicroscope, what we have already previously mentioned, so that we can observe them in this microscope, the erratic movement of the particles which are under the Brownian motion. They will be, this movement is actually present when the particle size is lesser than the 5 micrometers. Whereas the second phenomena and property is called as a diffusion. As a result of the Brownian motion, colloidal particles spontaneously diffuse from region of the high concentration to region of the lower concentration. So the rate of diffusion is expressed by the Fick's first law. So what that law says, the amount dm of the substance diffused in a time dt across the plane of area which is having surface area S is directly proportional to change in the concentration dc with the distance traveled dx. So this is what which is present. So dm by dt is equal to minus d into s into dc by dx, where the d, capital D, is diffusion coefficient. So the diffusion coefficient multiplied with surface area and change in the concentration for change in the distance. This will be given by the distance diffused in the time. This is what Fick's first law. So the minus sign, whatever which is indicated there, is the concentration, the diffusion is taking place in the direction of decreasing in the concentration, not against the increase in the concentration, because every system wants to get a equilibrium. That is the reason. Lower concentration getting filled with higher concentration zone, the movement is moving from the higher concentration to lower concentration. That is the reason it is given as a negative sign. But the amount which is diffused, which is not having any, that is a modulus of value, we are going to consider in case of calculations wherever we want how much amount is diffused. If you want to define the diffusion coefficient, it is given by the Stokes-Einstein equation, which is given here. T is equal to RT divided by 6 pi eta Rn. So the diffusion coefficient in the Fick's first law is further can be determined by using R. So universal gas constant, T is equal to temperature of the system. Fix, it is a numerical, pi is equal to 22/7. Eta is the viscosity of continuous medium, and R is equal to diameter of the particle or the colloidal system. What we have got, N is Avogadro number. This Avogadro number is a constant which is 6.023 into 10 to the power of 23 molecules per mole, which is present if we are considering a mole concentration which is having this many molecules. So we are going to have the value of R molar constant from the literature. We are going to keep it there. R is the radius of the spherical particle which is formed. Now you may get the question, sir, if I don't have the spherical particle formed in the colloid, in the micelle and in the case of emulsions, I am getting a globule which are spherical in nature, but I don't have such spherical in the solid particles which are having a irregular. That's what we have seen in the starting slides of colloids. It may be having a oblong, it may be having a needle shaped or flattened, or it is having a scaly surface. Because of that reason, what is required in this particular case is you need to take a surface area of the particle, whatever its shape may be, and calculate what is the equivalent surface area in the sphere and take the radius of it. You can put it there to find the diffusion. This is one way we can make it. This can be determined by using your microscopy experiment we are going to do in the practical. You are going to learn that equivalent diameter with respect to different shapes. So that part we will be seeing a little bit later in the practical also, you can learn. So R is the radius of the spherical particle at this particular juncture we are taking. If you see the above equation and analyze it, and we are going to get a different relationship between the different parameters. One is the velocity of the molecule will increase with the reduction in the particle size. When the particle size is more, it is diffused very fast. And the velocity of the molecule diffused increases with the increasing the temperature. Because in this particular equation, you have got T is in the numerator. That is the reason it is having a directly proportional relationship. And the velocity of the molecule decreases with the increasing the viscosity of the medium. When the viscosity is increased, and the velocity of the particle will be decreased. This is what we are observing in the picture. We are having eta denominator, eta and the R in the denominator of the diffusion coefficient. Because of that reason, you have got a inversely proportional relationship with your diffusion rate. The third one is osmotic pressure. Osmosis is a spontaneous net movement of the solvent molecules through the semi-permeable membrane. Don't get confused with the diffusion. Diffusion is a movement of a solid, whereas the osmosis, which is involving a movement of a solvent. These two phenomena are quite different. Whereas the Brownian motion, which you are having, when they are freely moved, allowed without any membrane, and we are not having any membrane, they will be moving as they like. That is actually what seen the first property, that is Brownian motion. So in this particular case, osmosis is a spontaneous net movement of a solvent molecule through a semi-permeable membrane into the region of high concentration in the direction that tend to equalize the solution concentration on the both the side. It means the solvent from the low concentration is moving towards higher concentration to equilibrate to the same concentration level. This is what we are seeing. So in that phenomena, what will happen? The solvent is tend to dilute your higher concentration region. It is keep on moving. So the direction, in the direction of higher concentration, you are going to have a inflow of solvent. In order to avoid that, you need to apply some pressure. So that external pressure required to be applied, that there is no net movement of the solvent across the movement, is called as the osmotic pressure. This type of phenomena will be existing in the case of colloidals also. This osmotic pressure is existing. So where do we apply all these concepts? Why do you want to study? This is actually what is our main question is. Most of the times we want to differentiate from the regular solution to the colloidal solution. The second thing in this particular case is, by using this concept of osmotic pressure, we can determine unknown molecular weight of your polymer. Polymer is the one which is having a chain reaction of a monomer. It is keep on going. You want to know the molecular weight of that particular polymer. You apply this concept of osmotic pressure there, you can determine the molecular weight of unknown compound or the polymer which we are getting. This is one major advantage. The osmotic pressure pi of a dilute colloidal solution is described by the Van 't Hoff equation. What the equation says, pi is equal to CRT. Pi is equal to osmotic pressure. T is the molar concentration of the solute. It means number of moles in 1000 ml of the solvent which are present. And this equation can be used to calculate the molecular weight of the colloid in the dilute solutions, because in the dilute solutions only this will be applicable to tend to equilibrium. And in the particular case of the equation of Van 't Hoff, if you are reading Van 't Hoff equation, in the C is replaced with the Cg by M. What is the Cg is increased, it is in the above equation, C is replaced with the Cg by M. The Cg is grams of the solute per liter of the solution. This is the concentration in the grams per liter of the solution. M is the molecular weight. So this you are going to have replaced with a molar concentration there. So you are going to calculate M if you are going to have remaining all parameters known. Like osmotic pressure, you know, by applying the pressure which is not having any solvent movement. R is known, T is temperature we are noting down. C concentration, molar concentration we are keeping there. So in that we are how many grams we have added, we know that we can calculate the M of the colloid what we are going to prepare. The fourth concept is called as a sedimentation. In the sedimentation, we know that in the coarse dispersion we are seeing, you won't get any sedimentation in these particular colloids because they are undergoing the Brownian movement. Now the question comes, sir, how can we know the sedimentation of these colloids? Is it possible? Under the normal conditions of the gravity, you don't get any sediment in the case of colloidal dispersions. But when you are using any higher centrifugal forces, then it can be possible. We will see now. So the velocity V of the sedimentation of the spherical particles having a density of the rho and medium density of the rho 0 and viscosity of the eta 0 is given by the Stokes law. So Stokes law shows that V is equal to 2R rho minus rho 0 G by 9 eta. So the velocity of the particle which are moving, which is moving down, 2R rho minus rho 0, that is the colloidal particle dispersion, that is density minus solvent density, and radius of the particle, G is acceleration due to gravity, and eta is equal to viscosity. If the particles are subjected only to the force of the gravity, then lower size limit of the particle obeys the Stokes equation is about 0.5 micron. So this Brownian motion movement becoming a significant and to offset the sedimentation due to the gravity and promotes the mixing instead. That is the reason you don't get any sediment when the particles are restricted less than 0.5 micrometer, because our colloidals are having particles less than 0.5 micrometer, that is 500 nanometer, and more than 1 nanometer. Because of that reason, you are having a Brownian motion. That Brownian motion causes the mixing. That Brownian movement causes the mixing means you don't get any sediment in the normal conditions of the gravity. But a stronger force, if you are applying consecutively, to bring all the sedimentation of the colloidal particles. So what is that one high speed centrifuge like ultracentrifuge can produce force about 10 to the power of 6. It can produce the force about 10 to the power of 6. So in the centrifuge, G is replaced by the W square X. What is the W square X? And acceleration due to gravity, we are replacing with the centrifugal force because it is dominating it. So it can produce, a normal centrifuge cannot be able to separate the colloidal particle to form a sediment. But in the ultracentrifuge, the force which is produced, the centrifugal force is 10 to the power of 6 times more than the gravitational force. Because of that reason, we are going to have the effect W square X. So in the W is the angular velocity or angular acceleration, and we are going to have this this value. You can calculate by taking the perimeter of your movement of your centrifuge, that is 2 pi times of the speed of the rotor in the revolution per minute, because you are having a 2 pi r is the path length, and you have got RPM rotations per minute, then your number of rotations you are calculating it, and you are fixing the time, then you are going to have how much is the velocity will be moved by that particular particle in the distance of the particle from the center of the rotation. So the x is the distance of the particle from the center of the rotation. You are going to have it. This is the angular moment W square. If you are replacing G with these values, your equation will be like this, what you have got. So the same equation what we have seen in the Stokes is replaced by the G, replaced with W square into X. This is what we are going to have under these conditions when your centrifugal force is 10 to the power of 6 more times more than your gravitational force, you are going to have a sediment formed in the case of colloidal dispersions. Otherwise, you don't get any sedimentation under the normal condition because of Brownian motion. The fifth one is viscosity. Einstein equation of the flow for the colloidal dispersion of the spherical particles is given by eta is equal to eta 0, 1 plus 2.55. So eta is equal to eta naught. What is eta and beta naught? Eta naught is viscosity of the dispersion medium. Eta is the viscosity of the dispersion. If it is present when the volume of the fraction of colloidal particle is pi. Generally, in the coarse dispersion, we are having a pi portion above 0.2. Generally, it is having above 0.2. 20% above, we will be having a solid dispersion. So the volume of fraction is defined as the volume of the particle divided by the total volume of the dispersion. In the case of 20% and more, then what will happen? 20 divided by 100, you are going to have a fraction of 0.2. So this 0.2, which is having an impact of a 5. So you are going to have in the colloidal dispersion less than 0.2 only, obviously, which is having a concentration in the lower level only. So that is the reason we are going to have the above equation converted into a relative viscosity. That is actually what you are doing, eta divided by eta naught. Then we are going to have Einstein equation is converted into 1 plus 2.55. And when you are taking this 1 to LHS side, you are going to have eta by eta naught minus 1. This you are going to have a specific viscosity, and which is equivalent to 2.55. And if the volume of the fraction represented by the concentration, most of the times it is gram per ml, like that we are representing in the cc, that is CGS units. Then n specific, that is specific viscosity divided by the c, then you are going to get 2.5. So now you have got a viscosity, relative viscosity, specific viscosity, and you are going to have n specific divided by c is called as a reduced viscosity. These four viscosities are very important to us, and we are going to determine them, and this will be helpful to determine the molecular weight of colloids also. What is the application of it? You can determine the molecular weight of colloids. So n specific divided by the c is equal to 2.5 in this particular case, what you have got by using the Einstein equation. But in your regular practical, when you are doing your online session also, there will be a model which will be given. You can calculate by using your data viscosity and relative viscosity. By observing with your sample with a solvent, you are going to get a relative. Then you are taking the same thing, eta minus eta naught divided by eta naught, you are going to get a specific viscosity. Specific viscosity divided by the C, concentration in gram per ml. Then you are going to get a reduced viscosity, that is called as n specific divided by C. Then you may get the question, why? What is the use of the that reduced viscosity? You can have that by plotting n specific divided by C versus C, that is C on the x-axis and n specific divided by C on the y-axis. You are going to get a line. That a line is extrapolated to the y-axis. Then you are going to get an inherent, that is intrinsic viscosity. That is fifth parameter. So these are all utility is required to know to get a molecular weight of any unknown compound. It is very much very important, crucial. If you don't know how many molecules of monomers are involved in the polymer formation, it is very much difficult. In those cases, these methodologies and approaches are very, very helpful to determine the molecular weight of colloidal substances. That is the reason you have got a separate unit, and you are learning and making these equations applied in the laboratory and assimilating this concept and using them in your curriculum also and competitive examinations. Where the C is a gram of colloidal particle per deciliter, you can take it, or ml cc, that is a cubic centimeter, you can take it. So under these concentrations, you are using very low concentration of colloidal only, but highly polymeric materials, we are going to use a Huggins equation is used. Specific viscosity expresses incremental of viscosity due to the presence of the polymer solution, and the intrinsic viscosity is a measure of the absolute contribution to the viscosity of the solution or limiting value of the specific viscosity by concentration at zero concentration. And what is this zero concentration? You can't get it. It can be evaluated, and you can make them calculated by plotting a curve. How to plot the curve? You need to get the intrinsic viscosity, as I mentioned. You need to take n specific divided by C at different concentrations on the y-axis and C on the x-axis. If you are getting a straight line, the zero, the intercept value is called as a intrinsic viscosity. This intrinsic viscosity is present in the square bracket eta. It is represented like that, and it has got utility. Why we are going to determine this fifth parameter? That is the question you are having in the mind. We have already got sorry, viscosity, relative viscosity, specific viscosity, reduced viscosity, and intrinsic viscosity. This intrinsic viscosity is given in the eta in the square bracket. Whereas the specific viscosity is the NSP, and whereas you have got a previous one which you have got is your relative viscosity is eta by eta naught. Then what is the use of this intrinsic viscosity? Intrinsic viscosity eta within the square bracket is equated to K into m to the power of A. This is the one which you are going to use. What is the K and A in this particular case are constants. They are the unknown constants. It means if we know m by other methods and eta, that is intrinsic viscosity by the laboratory, what you are going to do as a practical, then you can calculate K and M. Once you know the K and M, you can calculate unknown viscosity by putting the molecular weight, or you can calculate the molecular weight by putting the unknown intrinsic viscosity, known intrinsic viscosity. Any one parameter, if it is not known, you can calculate it. That is the one which you are using. Because there are four parameters are there. One is intrinsic viscosity, K and A constant, and another one is M. If you know three, remaining one can be known. In order to know this, first we need to calculate the K and A. For that purpose, you take the equation. That equation can be applied logs on both the sides. If you are applying the logs on both sides, what will happen? Intrinsic viscosity is converted to log square bracket theta is equivalent to log K into A into log M. If you see this, it is appearing as a y is equal to mx plus c, where if you are plotting this intrinsic viscosity versus log intrinsic viscosity versus the log molecular weight, then the slope will give a value A, and the intercept will give the K value. Once these K and A are known, you can calculate molecular weight of unknown compound by measuring the viscosity, or you can measure the viscosity without using an instrument and calculate by replacing M. That is actually what the utility of these properties. We are arriving it and getting it at the end after learning all of them. Why you are breaking our head and spending too much of time in this summer also is the reason is we are going to have a extraordinary tough concept which can be applied very simple manner, and we can determine their unknown parameters like molecular weight by applying these concepts. These constants are obtained initially by determining the eta experimentally for a polymer whose molecular weights have been determined by the other methods like light scattering or osmotic pressure or sedimentation. And we are knowing that, then we can calculate K and A. So once the K and A is known, then our job will be simplified. Then the specific viscosity for each fraction is determined, then the intrinsic viscosity can be calculated. And we are going to get the molecular weight of a given compound. So now we have seen the optical properties. Ultimately, at the end, what we have seen that we are going to have an advantage of calculation of molecular weight of them, even though they are having a polymeric chain reaction at the varying lengths, varying proportions of the chains, which we are going to have in the laboratory. So generally, we are going to have, after a particular point of time, we are going to have a chain terminating reaction to get a particular grades of material. But we need to know how much is the molecular weight which is already formed, which can be determined by applying these particular methods. The second property which we are after having an optical property and a kinetic property, the third property is electrical property of a colloid. Electrical property which will be having if sir 2 to 2:55 again class is going on. At 2:55 it will be I will be okay. So the colloidal particles acquire a surface. They will be having some surface charge because each colloidal particle is having an electrical charge. So when the electrical charge is present, when they are brought into the contact with the medium, they will be having a different concepts which we will be seeing now. Because each electrical property is based on the surface charge of each colloidal, what they are present. Obviously, our pharmaceutical powders are either colloid, which is having either weakly acidic or the weakly basic. So they are having a negative charge or positive charge. Sometime we are going to have a deuterionic effect, then we are going to have a neutral charge. This charge on the surface of colloid is very, very important to us for their stability and their properties, what we have already discussed. So one is the surface ionization. Here the charge is controlled by the ionization of the surface groupings. Because of that ionization on the surface, we are going to get a charge. For example, carboxymethylcellulose is present, which has a carboxylic acid grouping at the surface. When they are ionizing it, they give the negatively charged particles like COO1 minus. So COO has got one charged, negative charged species. Amino acids and proteins, they acquire their charge mainly due to the ionization of carboxylic acid and amino groups to give COO and NH3 plus ions. Because of that reason, they will be having a neutral charge. Whereas the quaternary ammonium salts alone, they will be having a positive charge. They act as a cations. So the ionization of these groups and hence net the molecular charge is depending upon the pH of the system. Even in the neutral system also, whatever the pH which is present in that system, it is having aligned to the ionization, it will be producing the charge. That is the reason pH is also very important in the colloidal stability. At the pH value below the pKa value of COO, so when the pH value is below the pKa value, dissociation constant, that is pKa value of COO, the protein will be positively charged. Because at that particular case, COO is present as unionized and it will be present as a positively charged. Because of the proportion of this group, COO is existing as a COOH in the pH of acid. The ionization of amino acid NH2 will be present as NH4 plus, which is having the higher pKa. That is the reason which is existing as a positively charged. Whereas at the higher pH, when the pH is higher above 7, the amino group is no longer ionized. It will not be present in the unionized form. Because of that reason, it is existing as NH2. There is no charge, but COO will be getting net charge. That is the reason the negative charge will be dominating in the ionization of carboxylic group. This results in the negative charge. It means If we are having alone functional groups individually, it will produce positive or negative charges on the surface. Even though we are having a zwitter ions in the amino acids and proteins, we are going to have a charged species at variations in the pH. Because of that reason, we are going to have some surface charge on the surface of colloids. This is called as surface ionization. At a certain definite pH, specific for each individual protein, the total number of the positive charge will be equal to the total number of the negative charge. That net charge will be 0. This pH is termed as isoelectric point of the protein. Then the protein is existing as a zwitter ion. At that particular point, the protein will be having a highest yield, and we are going to have precipitated there more, and we are going to get that particular protein easily coming out of the particular blend of mixtures. This concept which we are going to use it for the purification, this concept of isoelectric point, very important to remove a particular protein, because at that particular pH they will be having a least solubility. That is the reason they will be precipitated out and the yield will be more. If you don't apply this particular concept, your yield of the protein will be less. What is the protein? What is the yield of importance? Say insulin is a protein. You are going to give to the patient insulin. You are manufacturing a insulin. At the isoelectric point of a insulin, pH, isoelectric point, so you will be getting more yields of the insulin, means you can prepare the more number of delivery systems. So this ionization, surface ionization concept is very much important in the manufacturing systems to get the more yield. So the first, the surface ionization, which we have seen, and it will be having a ionization particle. Another one is an electrical double layer. After the surface ionization, how we are going to get a double layer? We have already seen in the disperse systems. In the surface, you have got one charged species like a plus, 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 plus like that, and oppositely charged ions will be attracted towards them, and you are going to have some charged species ion at the external layer or the nernst potential. After that, you are going to have a more number of opposite counter ions are going to get attracted to get a zeta potential. After that, you will be having a bulk of your solvent or a solution. Suppose some cations are adsorbed onto the surface of AA, giving the positive charge. These are all called as a potential determining ions. It may be an H2 plus in our case, 3 plus in our case of amino acids which are present in the alkaline pH, or which is having a positive charge. So the potential at the surface is called as a nernst potential. We have already seen. Then the counter ions are attracted to the positively charged surface by the electric forces, form the region called as a electrical double layer. And the double layer is present at the interface of BB and CC. In this layer, there are few ions than the free anions than the cations are observed onto the surface, and hence BB is still positive. Most of the times, this BB is still positive because they are attracting more anions, and some more cations will be present, but still it is positive. Beyond CC, the distribution of the ion is uniform and electro-neutral region will be existing. The potential at the BB is called as a zeta potential. It is defined as the difference between the surface of the tightly bound layer and the electro-neutral region. That is actually important to us. And if the zeta potential falls in the particular value, plus 30 millivolts and minus 30 millivolts, the attractive force exceeds the repulsive force and result in the aggregation of the colloids. I repeat, the zeta potential in the range of plus 30 millivolts to 30 millivolts in that region is present. If beyond that is present, they will be having a repellent force, and less than this and above this, which is having near to the zero, which is having attractive force, and you will be getting a aggregation of the colloids. The stability of the colloids is evaluated based on the zeta potential value of this plus 30 millivolts to minus 30 millivolts. So Zeta potential decreases more rapidly when the concentration of electrolyte is increased or the valency of the counter ion is higher. This we have already seen in the previous course dispersion also. So this is actually what is seen. And also another concept is called the DLVO theory. We have already applied there. And this is also based on the electrical double layer only. This electrical property of this colloidal we will be learning in the next class in the depth again. And we are going to concern with, because this is very important concept. The same concept what you have learned there is applicable here also. If anybody is having a doubt now, they can unmute themselves and ask.